So continuing with this exercise, let's look at delta x, okay? In our case, delta x, as before, it's going to be x sub n minus x sub 0 divided by n, but x sub n, the final value is 1, the initial value x sub 0 is 0, so delta x is 1 over n. Okay, now next we'll try to identify the different values of x sub I in this sigma notation. So let's start with x sub 1. We know what's x sub 0. It's 0 and x sub n is 1. What is x sub 1? It will be x sub 0 plus delta x, because every x value is the previous value plus delta x plus the width of the interval. So it will be 0 plus 1 over n, or simply 1 over n. X sub 2 will be x sub 1 plus delta x, and it will be x sub 1 is 1 over n, delta x is 1 over n, so we have a total of 2 over n. And you can see quickly how this pattern, how a pattern is being developed. X sub 3 is x sub 2 plus delta x, so we are looking at 2 over n plus 1 over n, or 3 over n. And if you continue, then you can conclude that x sub I will be I over n. And to verify that this is correct, go on and put x sub n, and if I equals n, then you have n over n. Indeed, it's equal 1. So this is just a check. So we start at 0. X sub 0 is 0. We can see it here. And then we end up at 1. So we know that this is the important part, that x sub I is I over n. Also, we need to find out, we need to provide the expression for f of x sub I. Okay? X sub I, let me rewrite it, is y over n, and therefore f of x sub I, which is x sub I squared, becomes I over n squared. Okay? So, what is R sub n, the sum? R sub n, we left it right here with the sigma, right? So it was the sigma, R starts at 1, goes to n, of f of x sub I times delta x. And now we're going to replace. So we figure out that it will be the sigma 1 to n. Instead of x sub I, we're going to write I over n squared. And instead of delta x, we have 1 over n, like so. And this is what we need to deal with. Okay, take a deep breath here and think about what we are looking at. In this expression for R sub n, what varies inside the summation? The only quantity that varies is not n. Remember, n is the fixed number. As is a finite number, is the number of sub-intervals that we're going to use. The only thing that change is the index I. I can be 1, and then 2, 3, 4, all the way to n. For example, if n equals 10, then I will go from 1, 2, 3, all the way to 9, and then 10. But n itself is going to remain 10. What it means that we can pull it outside the sigma notation, because if n is fixed, you have n squared times n, or n cubed. That doesn't change. It will be always 1 over n cubed. And what we have is the sigma I varies from 1 to n of I squared. Like so. Okay? Now look at the handout. Do you have an expression for the sum of I squared? You don't have it for I, but you do have it for k. Look at the bottom next to the one before last. You see on the handout, you see the sigma when k goes from 1 to n of k squared is n times n plus 1 times 2n plus 1, all of it divided by 6. There is an easy proof that shows this result. It's one of the indices, it's an index in the textbook. If you like me, I can write it up and post it on the website. But this is the end result. We're going to have, for r sub n, we have 1 over n cubed, right? And then we have the result of the sigma, which is n times n plus 1 times 2n plus 1, all of it divided by 6. Okay? Now this can be simplified a little bit. We have n divided by n cubed, so that will be n squared in the denominator. So the denominator will be 6n squared. And the numerator will be n plus 1 times 2n plus 1. The next step on the next page, I'll clear the parentheses. I'll FOIL this product of two binomials. Okay? So let's rewrite the last line. R sub n, we end up having n plus 1 times 2n plus 1 divided by 6n squared. Clear the parentheses and get n times 2n is 2n squared, 1 times 1 is 1, and in between we have n times 1 plus 2n, so 3n in the middle. Now, this is R sub n. This is the right-hand sum. Folks, this is not an exact value. This is not an evaluation. This is still an estimate. How we evaluate? Well, I think Matt and Kelton said it earlier when I asked you how we can improve, I think it was Kelton, how we improve the evaluation of an area. Said, let's take infinitely many intervals, or let's divide the interval 0 to 1 into infinitely many divisions. So we evaluate, that's right, we evaluate the area by dividing, evaluate, dividing 0 to 1 into infinitely many intervals. Okay? In other words, we're going to let n go to infinity. Okay? On the other hand, you said as well, as n goes to infinity, delta x goes to 0. Okay? So, what happened is the area really won't be r sub n, but it will be the limit as n goes to infinity of r sub n. And you thought you were done with the limit, didn't you? But this is an easy limit. This is a limit at infinity, and this is the limit of, as n goes to infinity, of 2n squared plus 3n plus 1 over 6n squared. What will be the first thing to do? I'm sorry? Factor by n squared and then, divide both numerator and denominator. So it will be the limit as n goes to infinity. Let's factor n squared from the numerator. So you have 2 plus 3 over n plus 1 over n squared. And then n squared from 6n squared, you have n squared times 6. And we simplify it, and we end up having the limit of 2 plus 3 over n plus 1 over n squared over 6. And now by direct substitution, 3 over infinity is 0, 1 over infinity squared is 0, and you end up having 2 over 6, and this is 1 over 3, and this is the precise value of the area under this curve. So this is an aha moment, I think, where you actually come with the precise value.